Of the course on industrial automation and control. So in this course, in this lesson, we are going to start at level 0 of the automation pyramid, and in particular we are going to look at measurement systems or sensors. So before we are going to look at these measurement systems for a few lectures to come. So before we do that, let us first look at a general measurement systems and try to understand its characteristics. So that's precisely what we are going to do today. So in this lesson we are going to look at measurement systems characteristics, and the instructional objectives are the following. First of all, the most important thing is to learn is what is known as the static characteristics of sensors and instruments, and then understand what is meant by calibration, and how do we characterize errors, describe the response of first and second order sensors to dynamic inputs, that is most important for control, and finally look at some industrial sensor specifications. So let's first look at the general structure of a measurement system. So all measurement systems can be thought of being made up of one or more of these blocks. So here is so here we have the actual measure end, whatever signal we are trying to measure, pressure, temperature, that is the signal which is affecting the sensing element. So there is a sensing element. Actually sensing is a process of continuous energy conversion from any form depending on what we are trying to measure. So from mechanical form or from thermal form or from optical form to finally to an electrical form and then the electrical form gets finally transformed further to digital forms, etc., before their output. So through these blocks that conversion takes place. So here you have the measurement or the input, which is the true value. So the real pressure or the real temperature, which is the sensing element which exists at the sensing element. Then the sensing element does the first round of conversion and brings it generally to some sort of an electrical form, either in the form of electrical parameters like resistance, capacitance changes, or in the form of voltages and currents, which have to be further manipulated by electrical circuits called signal conditioning elements, and sometimes amplified, sometimes the conversion from resistance to voltage. So generally at this level it is in a standard electrical form of voltage, but then some further signal processing goes on to remove noise, to make it linear and things like that. Some of it can be analog, some of it can be digital, and then finally it goes to the data presentation element, or where the data is utilized. It can be presentation or application element. So it can be a display, or it can be a recorder, or it can be a controller. So this is the general structure of a measurement system. For example, if you take an example, for example, here is a weight measurement system. So the input is the true weight, which is sensed by a mechanical member called the load cell, which converts it to strain. That is sensed by another member called a strain gauge. We will see all these sensors in our future lessons, which converts it to a resistance form. So you see that even there are two sensing elements. The first sensing element converts weight to strain, the next one converts strain to resistance, and then we feed it to an electrical circuit called the Wheatstone's bridge, which converts this resistance change to a low level voltage, millivolts. So this is these are signal conditioning elements. Then it goes to an amplifier, which amplifies it to standard voltage ranges like 0 to 10 volts. Then it goes to, if we most often it is very convenient to have digital signal processing, so we can make it through an AD converter, then input it into maybe some microcomputer and do some digital signal processing, and then finally send it to in this case a display. So you get a digital display of the reading along with units, right. So that is some more data processing. So this is how real measurement systems looks like. So it is basically a cascade of several blocks, including the sensor, the signal conditioner, plus some computing elements like the signal processor. So sensing is actually extremely important in automation from various points of view. Firstly, in product quality control, because the product quality is actually assessed by sensors themselves, by some sort of instruments. In process control, so if you have a rolling mill and if you want to control the roll thickness, then your feedback or all process control is actually closed loop feedback control, about which we are going to learn in the future lessons. So for that, a critical element is the feedback element. So the variable which is being controlled, it may be thickness, it may be temperature, whatever, has to be continuously fed back using a sensor in the sensor of the control system, and the performance of the control system is actually critical to that of this to the sensor. So sensing is of primary importance in control. Then process monitoring and supervision. So all kinds of coordination between machines, then fault detection, safety measures, all these can be done, plus providing energy efficient optimal set points. For doing all this we need sensors. And finally we also need sensors for manufacturing automation. So as we will see when we will see how the manufacturing automation systems can be put together using let us say programmable logic controllers, then you will find that they use various kinds of sensors extensively, sensors like limit switches, pressure switches, contacts, etc. So so sensing is extremely important in automation. Now, so in this lesson we are going to see that if you look at a sensor as an abstract element which gives you a value, which gives you the information about a physical quantity, then we need to know how to characterize the behavior of this device called the sensor or the instrument. So we need to understand about instrument characteristics, and instrument characteristics can be of two types. The first is the static characteristics. Static characteristics implies that of an instrument are concerned only with steady state readings. So if you it says that if you apply a 1 volt signal, do you get a 2 volt signal? So we are just saying that if we apply, let us say to a temperature sensor, if we apply 100 degree centigrade, what is the output voltage? Now we are not concerned with the fact, when we are discussing static characteristic, is that how the temperature came from whatever was, let us say, the room temperature 200 degree centigrade, how much time it took, what was exactly the way the voltage rose. We are not asking about these things. We just want to know that if you apply 100 degree centigrade, eventually the temperature settles at what value. So that would be a static characteristics. Now static characteristics are important for indicating instruments, because indicating instruments are generally concerned with steady state values, or for instruments where the dynamics is actually very fast, that is, this settling from whatever was the temperature to the 100 degree centigrade temperature is so fast that for all practical purposes we can neglect the way the temperature rose. That does not concern us. So in such cases the static characteristics is of importance, while there are cases where dynamic characteristics is also important, especially in control, because as we shall see later that the performances of control loops, for example, when you are trying to control, the essence of feedback control is that, suppose you are saying that this temperature should be maintained at 100 degree centigrade. Now if the temperature sensor has a 2 degree centigrade error, by which I mean that suppose when the temperature is 98 degree centigrade, the sensor is telling you that it is 100 degrees centigrade. It is giving you a wrong information which is wrong by 2 degrees. Then the controller has no way of knowing the actual temperature 98. It actually thinks that it is 100 degrees centigrade and it tries to maintain it at that temperature, while the actual temperature stays at 98 degrees centigrade. So you have a steady state error, right? So you have a real error, that is that physical real temperature will be 98 while the controller will think that it is 100. So such errors occur due to controllers and due to errors in sensors, number one. And number two is that now these errors can sometimes be reduced by designing the gains. So it sometimes happens that we need to not only maintain fixed temperatures, sometimes we need to track temperatures. So in such a case, if we don't get the readings as they are existing, then what happens is that the temperature develops what is called a phase lag, that is the controller develops a phase lag, and it will not be possible to exactly track moving commands. So in such cases, dynamics of the sensors are actually important. So we will look at both sensor and both static and dynamic characteristics, and before we look at this characteristic, we need to understand how they are obtained. So they are actually obtained by a process called calibration. So basically a calibration is, we are saying that if the true value is so and so, what is this? So calibration is basically, when you say characteristics of an instrument, what you mean is what is the input output characteristic. So if the true value is so and so, what is the output? That is what is essentially to be determined. Now the point is that the true value can never be known. So therefore, how do you assess the true, how do you get the true value? So essentially what we have to do is that we have to measure the true value again using some other instrument, which for scientific and technical reasons we actually believe to be much more accurate. So it's always, calibration is essentially a comparison between the instrument that is being calibrated and another instrument which is assumed to be the true value. So such instruments, depending on the calibration situation, for example, if you are calibrating, there is actually a calibration chain, in the sense that when you are calibrating some instrument in the factory, it is not possible for all variables. There are some very, very accurate instruments which are maintained in under special conditions in national standards laboratories. But when somebody is calibrating, let's say in a shop floor, it is not possible that every instrument will be calibrated against the national standard. So therefore, there are secondary and tertiary standard equipment. So anything will have to be calibrated against such an instrument. So that's what it says, that with either a primary standard or a secondary standard with a higher accuracy than the instrument is to be calibrated. So this is the essential scenario, that you have a this is the sensor instrument which is to be calibrated. Now the reading, first of all you are look at the fact that this is the measurand which you are measuring using some standard instrument, and you are thinking that this is the true value. This is an assumption. You are also measuring here this is not required. I don't know why this is connected. This diagram is drawn wrongly. So the sensor instrument under calibration is giving a measurement. Now this measurement, again, for example, suppose it is a voltage, then how many volts it is, that again will have to be measured by some instrument. So that may be this instrument, right? So in that sense this is required. So you have to measure the measurement. If the measurement is, for example, given in a digital form, then you don't need to measure it. Then you can, so this may be there or not there. On the other hand, there are, this sensor, this instrument reading or the measurement is actually a result of not only the measurement. It is a result of many other factors. For example, it may be a result of temperature. For example, if you take the weight measurement case, then the strain gauge resistance change is not only a function of the weight you put, it is also a function of the temperature, because every resistance has some temperature coefficient. So if the temperature varies, then the resistance is going to change. Similarly, there are various kinds of interfering inputs, like for example, there may be some noise, there may be some noise induced from a power supply, or from some power line, or especially in the industrial environment, there are plenty of noise sources, and these signals can also affect the sensor measurements. So generally, when you, to the extent possible, when you are trying to calibrate an instrument, you will have to also note what are the, for example, what is the temperature. So if you, so that you can actually apply the corresponding corrections, and you can characterize, when you are trying to characterize the instrument, you will also have to characterize its response with respect to these kind of inputs. I mean, in some cases it may not be possible to measure these kind of interfering inputs, and in such cases we try to ensure that these interfering inputs are not present. So we do shielding, we actually do take it to a different setting and actually try to see what the sensor is doing. So essentially we try to measure the measurand, we try to also measure the output of the instrument, and we try to measure modifying inputs like temperature, and then we establish the characteristics of the instrument. So since the instrument must have been constructed to be, you know, relatively unaffected by modifying inputs, so I mean generally what is of much more importance, of primary importance, is to see how the instrument characteristics are dependent on the measurand, right. So that is what we are going to look at mainly now. So, so this is what it says, that this is what I was talking about, that there are different standards of instruments. So the instrument to be calibrated can be calibrated against a laboratory standard. Now the laboratory standard instrument also has to be from time to time calibrated against, you know, other standards like, you know, secondary standards which are special instruments which can be, you know, existing in some test houses, and then so you from time to time you have to send these instruments to the test houses and get them calibrated. On the other hand, these test house instruments again have to be calibrated against, you know, some very accurate national standards. So in this way you have, you know, what is called a chain of standards of increasing accuracy, and at different levels you always calibrate according to a with respect to an instrument which is at the next level according to the chain. These static characteristics. So we begin with span. So it says that if in a measuring instrument the highest point of calibration is x2 units and the lowest point is x1 units. So what we are trying to say is that the instrument has been used between 2 points. So the instrument has been calibrated to work between 2 points, right? And this is so this is x2 and this is x1. Then the instrument range is x2. It is the highest, so it can work up to that value, and the span is x2 minus x1. So if this is 200 degrees centigrade and if this is minus 40 degrees centigrade, then the range is 200 and the span is 240, right. So that is pretty obvious. So we have to remember these two details. Next, let us talk about one of the perhaps the most important parameter called accuracy. So accuracy, if you see instrument specifications, they will be generally written as accurate to within x% of either reading or span. You know, sometimes they say reading, sometimes they say span. In fact, sometimes they also mention constant values, that is accurate within plus minus 1 degree centigrade. So when this constant value, then since the span is a constant quantity, so you can always express it as a percentage of span also, right. So if the span is 100 degree centigrade, then an error is of plus minus 1 degree centigrade can be expressed as 1% of the span. So it's either a constant value, it may be expressed as a percent of span, or it is a percent of the reading. Okay. So what it means that if a reading is 100 and if it has plus minus 1% of, let's say, span accuracy, then the reading is somewhere within, let's say, 99, and then the true temperature will be between 99 and 101 degree centigrade. And this, so at all points, so whatever reading you get, you can always, basically these are needed because the user of the instrument needs to know that within what values, so it gets a reading, but within what is the guarantee that the true value will be staying within certain limits. So that limit is stated by accuracy. But then again, the true value is unknowable, and it is actually what is stated is that with respect to the calibration. So then the next point is linearity. You know, we generally want, although instrument calibrations will not strictly follow a linear curve, but still it is very useful to imagine the system as a linear one. So you know, if you have so that you can very easily interpret the true value. So if you have an instrument sensitivity of, let us say, 10 millivolts per degree centigrade, then if it gives a 25 millivolt signal, then you know that it is that the temperature is 2.5 degrees centigrade. So you can get it just by dividing by a number or sometimes adding another number to it. So it is from that point of view, from the point of view usability, it is very attractive to express the characteristic as a linear one. But then it is not linear. So therefore, while you mention a line which can be used for deducing the true value from a reading, you also have to give some bounds within which the true value will remain, because it is not exactly going to, because the instrument does not actually follow that line characteristics. The line is only an approximation. So when you are telling the user to use the approximate model of the line for simplicity, you also have to tell him what is the kind of error that he or she can expect if she uses the linear model of the instrument. So that is given by the measure of linearity. So the linearity specification indicates the deviation of the calibration curve from a good fit straight line. So now how do we obtain this straight line? We can obtain the straight line in various ways. So one way would be this, that you actually perform some calibration experiments. So you got these data points. So you got these data points, these are experimentally obtained. So for all you know, the true characteristic of the instrument, let me use a white color, that will be good. So for all you know, the true characteristic of the instrument may be like this, and you are approximating it by the straight line. So you have to also say that while if you use the straight line characteristics, then the true value is going to be within which limit. So that's why when you say linearity, actually the linearity specification is actually a non-linearity specification, in the sense that it indicates deviation from linearity. So it is defined as the maximum deviation of an output reading from a good fit straight line. So obviously you want that. So obviously you want that the straight line, that the linearity specification is small, so that you are telling that if you use that straight line characteristic, you are not going to have much error. That's what you are telling to the user. So that it is the smallest possible, you have to actually take all the data and make a best fit straight line such that the sum of square of errors is the least, or something like that. So that's linearity, that it is the deviation of the calibration data from some good straight line which you have obtained either by data fitting, or in some cases it may be obtained also in a different way. So for example, in this case you can also obtain it, that's a simpler way, by taking the reading at the least value and the maximum value, and then simply assuming that the characteristic is going to be like this. Now this is not the best fit line, probably for this curve the best fit line would have been like this. However, in some cases you can perhaps use this line, that's actually a simple thing if it does not matter. So basically nonlinearity, whatever is the line, once you have fixed the line, the nonlinearity is actually this deviation. So here it has a maximum deviation. So the nonlinearity spec, or which is, I mean, we actually refer it to as a linearity spec, is actually deviation from that line, right. So next we are interested in sensitivity. So sensitivity is actually the slope of the line. So if you have a calibration curve and then, so that will be the sensitivity, and if you have a calibration curve and then get a straight line, in case you have a linear characteristic, it will have one single sensitivity. If it is very nonlinear, then sometimes you may also express it as, so you can do various things. You can express, say, let us say 3 sensitivity figures. So one sensitivity figure will apply in this range, the other sensitivity figure which is the average slope of the line in this range, and then another sensitivity figure which will apply in this range. Or you can, so basically sensitivity is the slope of the characteristics. So depending on the nonlinearity, you can use multiple slopes on multiple ranges. Sometimes instruments do that. Similarly, we are also interested in what is called repeatability or precision, in the sense that we don't want that today we make a measurement of the temperature of boiling water, so it is giving me some reading. Tomorrow if I take that reading should be nearly same. It may not be exactly same, but it should be nearly same. So when it is very close, if you take multiple readings, if they are very close, then the instrument is said to be repeatable or precise, right. So repeatability of an instrument is the degree of closeness with which a measurable quantity may be repeatedly measured, right. So we go to the next one, which is resolution. This is also very, it says that how much of change in input will actually cause a detectable change in the output. So what is the smallest change in the input? So can we detect a change of 0.1 degree centigrade, or can we detect a change in 0.01 degree centigrade? For example, if you have a clinical thermometer, then you cannot possibly detect a change of 0.01 degree centigrade or 0.01 degree Fahrenheit. Generally they are calibrated in terms of Fahrenheit. So that is the resolution. If a temperature transducer is resolution is 0.2 degree centigrade, then it is the smallest temperature change that can be observed. Okay. Similarly, we have, similar to the concept of dead zone, sometimes sensor systems will have dead zones. For example, we often find that these electrical meters, sometimes they will stick. Any mechanical arrangement tends to develop something like a static friction, which also depends on many things like temperature, time, humidity, and other things. So what happens is that till say if you have an ammeter, then till you send a certain amount of current, the torque is not enough to overcome static friction, so the needle does not move. So dead zone is the largest value of the measured variable for which the instrument output stays 0. So from 0 to that value, there is going to be no deflection, no reading, nothing. So that is called a dead zone. So what is the difference between the dead zone and the resolution? Dead zone is actually the resolution from 0, while resolution can be resolution from 24 to 24.1, 24.1 to 24.2, while generally dead zone is referred to from 0. So it occurs due to factors such as static friction. Similarly, sometimes we have hysteresis in instruments, so that if we have an increasing sequence of input values, if we are increasing the input from, let us say 0, 10 degree centigrade, 20 degree centigrade, 30 degree centigrade, they are increasing sequence of values, then we get one set of readings. while if we have a decreasing set of values, then we get another set of readings, and these readings are distinctly different, right. So in that case we say that the instrument has a hysteresis. It can occur due to various factors like gears, gear backlash, or it can occur due to magnetic components, or sometimes due to hysteresis which occurs due to elasticity. So due to such things the hysteresis can be there. So so this is the figure that we are saying that if x is increasing, then the readings that we obtain follow this curve, while if x is decreasing, they actually follow a distinctly different curve. So if such behavior is demonstrated by an instrument, it is said to have hysteresis. So next, now the errors that we have, so we have actually typically an instrument is supposed to have a calibration curve, but the reading that it has may not exactly match with the calibration curve. It is if you read out an ammeter, then it has some scale fixed, but if you send exactly 1 ampere current, then the needle may not stand at 1 ampere. So this is the error. Now the error is typically characterized as into two different kinds. So since the instrument is actually assumed to be a linear instrument, so it is assumed that the error can be of two types. The first type is called bias or offset, which is a constant error which is going to stay throughout the range. So maybe when you have a reading of, when you have an actual current of 2 amperes, your reading shows 2.5. When you have 3 ampere, it shows 3.5. When you have 10 amperes, it shows 10.5. So you have a 0.5 ampere of bias, right. If you see ammeters, normal ammeters, you will find that such biases can be corrected by screwdrivers. They are also sometimes called zero adjusts. Similarly, there can be a gain error. So you have a sensitivity, while we have a nominal sensitivity which is indicated by the scale, and your actual instrument sensitivity may actually deviate from that, and then you have a sensitivity or gain error, and the error in reading due to this gain error is going to be proportional to the reading. So if you are measuring 10 degrees centigrade, then the error due to gain error is going to be half of what you measure due to 20 when you measure 20 degrees centigrade. So we assume that the errors are of two kinds, and these typically in typical sensors and instruments, very often they can be corrected by electronic signal conditioning means. So that's what is depicted, that if you have a zero error, so that's a bias, and if you have a slope error, that's your gain error. Next is drift. So sometimes what happens is that even if you correct at some point of time during calibration, even if you correct for the bias and the gain error, you have drifts in the bias and the gain. So again, such bias and gain errors can develop due to variations in temperature, variations in time, or some other conditions. So the rate at which these will develop are characterized by a performance characteristic called drift. So typically drift is characterized for temperature and time. Now we come to, so this more or less completes our static characteristics. So generally talks about an input output curve, right? That is a calibration curve. So there is no time here. If we give an input, we will get an output in the steady state, and we are only talking about the characteristic between this input and the steady state output value, right? But we have to talk about dynamic characteristic of the instrument when the input is not steady. So the input is continuously changing, and the dynamic response of an instrument to an input signal is typically modeled in terms. So now we have to worry about that if the input signal suddenly changes from some value to some value, how is the output signal going to change? So we are not only concerned with the new steady state value that the output signal will achieve, but we are also concerned with how it is going to achieve that over time. So when we talk about such characteristics, we talk about the dynamic characteristics of instruments. So accordingly, we have various kinds of instruments. So we start with the simplest, which is the zero order instrument, whose characteristic is given by y equal to kx. So it is assumed that for the kind of inputs that are relevant to that sensor, the output is instantaneously equal to the input. So it's like a resistance, you just apply a voltage, you immediately get a current. So the input output ratio is linear, and this linearity exists from instant to instant, right. So it is for such instruments there is no dynamics, and the static characteristic is the only characteristic that you need to see. So such instruments are called zero order instruments. For example, typically, a potentiometer, I was talking about a resistance, right. So a potentiometer is nothing but a resistance. So for a potentiometer, the position signals, potentiometers typically measure position, so the potentiometer will be connected to this variable point. So as the variable point moves, the voltage that you will get will be directly proportional to the position, right. So in this case there will be instant to instant, and since the position is actually a mechanical variable, so therefore there is not going to be too fast a movement. So as far as the electrical behavior is so fast compared to that you can just assume it to be a pure resistance, and then you have what is known as a zero order characteristics. So the output voltage will be directly proportional to the displacement theta. Let us say angular displacement. In this case, if potentiometers can be angular as well as linear. So there is a sensitivity called of the potentiometer is volts per radian. On the other hand, there are some kinds of instruments where if the input changes suddenly, the output cannot change suddenly. The output takes some time to rise. For example, let's take temperature measuring instruments. For example, thermocouple. Actually, a thermocouple is typically, as you will see, it is not wherever it is making the measurement of the temperature. Maybe it's steam. Then the bare thermocouple is actually not inserted into the steam, because that will damage the sensor. It will degrade fast. So it is actually put inside a tube. So you can imagine that even if there is a temperature change outside that tube, which is called a thermo well, so it's a tube, inside that you have the thermocouple. So even if your your environmental temperature which you are trying to sense, even if it changes, some time will be required for this temperature to actually flow through there has to be heat flow through the insides of the thermo well into the thermocouple junction before an EMF can be developed. So because of the thermal properties of this thermo well, there is going to be some time required. So even if you suddenly fill this space with, let us say, steam, the temperature of the junction of the thermocouple will not instantaneously be equal to the temperature of the steam, but it will slowly rise, right. So for such transducers, we have a first order instrument character, first order or second order. So that will depend on the modeling of the thermocouple. But so typically first order instruments are transducers that contain a single storage element and can be modeled of first order. So for such cases, the output value actually obeys some kind of a differential equation which is of this type, and where tau is called the time constant of the system. So if tau is larger, then the system slowly rises, while if tau is short, then the system is fast. So we can easily compute the response of a sensor whose input is a step input. So let us try to characterize the response of this kind of a sensor to various kinds of changing inputs. So these are two examples: mercury in glass thermometer and thermocouple in a thermo well. So if you have a step input, so the first kind of input that we consider is a step input. So step input means it is at 0 and then suddenly it rises. So at t is equal to 0, the input is 1, suppose. So then actually we can compute that the time response or yt is going to be such a function of time. So the graph will show what kind of a function it is. So you see that it will gradually rise and then it will become 1. So if you have a large tau, it will rise slowly. If you have a small tau, it will rise fast. So this is tau decreasing, right. On the other hand, as we all know, I mean, the response to a dynamic sensor to arbitrary inputs is of interest, because if such a sensor is actually put in a control loop, all kinds of it is not going to be regular as a step input. So we sometimes, since we know that any arbitrary waveform, most arbitrary waveforms can be thought of as a sum of sinusoids, sine and cosine waves. So it is very useful to actually characterize the behavior, that is the response of the instrument to a sinusoid of different frequencies. So this is called a frequency response, and this is very important for an instrument. So if we have a sinusoid, so this is my instrument. I am applying an I sin omega t. Typically what will happen is that if the instrument is supposed to be linear, then you will get, as output also you will get a sine wave, but that sine wave magnitude will be higher, will be different from the magnitude of the input wave, and it will also develop a phase lag. So it is this, so we actually try to study two things. Since the frequency is going to remain constant, so the frequency need not be studied, it is the input frequency itself. But the ratio between the output magnitude and the input magnitude, which we call the gain, and the phase lag, these are the two things that we typically characterize. So this is a mathematical solution. So for example, the gain over different values of frequency actually varies like this. So you can understand that if the frequency is too low, then the gain of that is 1, because so the frequency is too low means you are giving a slow sinusoid, which means that the instrument can always come to steady state and it can get the value of the input. On the other hand, as the input frequency increases, so before the output of the instrument can really rise, the input changes. So the output of the instrument can never rise enough, and therefore the gain falls. So this is the frequency characteristic of an instrument. Similarly, if you have a phase plot, then it turns out that as you go for higher and higher frequencies, the phase lag increases, and the maximum phase lag possible for a first order system can be 90 degrees, so it will gradually approach 90 degrees. Now sometimes we also have to model the systems as a second order instrument or sensor. This choice can actually depend on which kind of model you will use. That may depend on physical reasons, or it may depend on the kind of response that you actually get from the instrument. So some instruments are rather assumed to be governed by a second order differential equation. For example, accelerometer, anything which has mass spring damper kind of representation, and we'll have second order dynamics. So its dynamics, its input output dynamics is given by a second order differential equation as shown, in which there are two parameters. One is called a natural frequency, another is called a damping factor. So again, its response to the step input, in this case we have three kinds of cases depending on what is the damping factor. So one case is when the damping factor zeta is greater than 1, in which case we call it an overdamped system, and this is the expression for the output time function. We will just see the case and then we will see the plots. So and then we have a case when xi is equal to 1, zeta equal to 1, which is called the critically damped case. Here and the last case is when we have xi is less than between 1 and 0. So, that is called the underdamped case. So, the plot actually looks like this. So, this is of interest to us. So, you see that this is the step response. So, the input applied is this is the input. Now, for different values of zeta, for example, if as zeta goes to lower and lower values, you can see that you get an oscillatory behavior. So, there is an overshoot, this is called an overshoot. So, for underdamped sensors you are going to get an overshoot. On the other hand, for overdamped systems there is no overshoot and it slowly rises just almost like a first order system. Similarly, if you see its response to a sinusoidal input, again you will find that these are the expressions. So, you get a gain and you get a phase shift, and this is the expression for, this is the plot for gain. So, you see that the gain actually changes with frequency, right, and for underdamped systems the system tends to resonate. So, this is the resonant frequency. So, if you give a sinusoid close to the resonant frequency, then you get a huge output, right. Well, on the other hand, for overdamped system there is no such resonance. So, you have similarly the phase, if you see the phase, the phase plot looks like this again with frequency. So, towards low frequency the phase tends to stay small, and as frequency increases, so the maximum phase that can occur is 180 degree. So, these are the phase lags. So, we have seen the static and the dynamic characteristics of sensors. Now, let us see some example specifications. So, this is for example an industrial thermometer. So, see what it says, what all are stated. So, first of all it is based on a thermocouple, therefore, the type of the thermocouple is stated. We will see what the type of thermocouple is, but interestingly the range is given. So, you see this is the minimum and the maximum values in which this thermometer can be used with these given specifications. So, if you use it within this range, then you will get a resolution of 1 degree Fahrenheit or 1 degree centigrade, and etc., etc. So, whatever specifications are given are valid within this range. So, in this case range is 1370 and span is 1440. The resolution is 1 degree F or 1 degree C, actually it is whichever scale you use, because actually the resolution of the basic sensor is the same, while actually it is depending on the scale that you choose, you can have different kind of electronics. So, the resolution also varies. So, it says that the resolution, so here it is stated as 1 degree centigrade. So, the minimum change that can be observed, which can be detected by the sensor, is actually 1 degree centigrade. Calibration error standard. So, all these specifications are actually with respect to a certain, this DIN is actually the German standard, BS is the British standard. So, similarly it says that the meter accuracy at 25 degree centigrade, that is when the ambient temperature is 25 degree centigrade, is 0.2% of reading plus minus 1 digit. This plus minus 1 digit comes because you are going to have a digital display. So, we see that in digital displays there has to be there is an effect called quantization, and therefore, this plus minus 1 digit error comes. So, basic accuracy is 0.2% of reading. So, in this case it is stated as in terms of reading. there are some other, apart from these kind of specifications, there typically if you see an example industrial specification, you will find some other things like which are specific to the which are specific to the particular sensor that you are using. Now since thermocouples use long wires, so there is a series mode rejection. Series mode rejection means that typically when thermocouples are drawn from long wires, so they typically tend to catch series mode interference, especially at the power frequency, because there may be power lines and they will add power frequency interference as a series voltage. So it says that the sensor is so constructed that it can actually reject that 60 hertz such voltages which are induced. Similarly, zero drift, it says that even if the zero drifts, every time possibly this instrument will have a button, and or maybe every time this instrument is commanded to take a reading, it will first automatically make it 0. So so there is an auto zeroing facility. The environmental temperature range is, so there are all these specifications are to be, this sensor is to be used in such a range, and the size and weights. Okay. Similarly, another thermometer another temperature thermometer, again based on thermocouple, again it has some ranges. So we have already seen it. Look at its accuracy reading. It says that below 230, so you see that below 230 degree Fahrenheit, above minus 150 degree centigrade, this is its accuracy statement, while below that this is its statement. So here it is stating it in terms of reading, here it is stating in terms of a constant or a percent of span. Similarly, it says that in some other mode called a differential mode, this is the kind of accuracy, plus minus 0.3 degree centigrade over a plus minus 100 degree centigrade span. So you can see that typical such industrial instrument specifications will include this kind of parameters. For example, resolution is 0.1 degree, and above 999.9 degree it is 1 degree. The other things are battery housing. These are specifically, battery is important, especially when you have a portable instrument. So let's look at another sensor, which is a flow meter. Now there are so many specifications. The important ones are, say, accuracy and linearity is plus minus 1% full scale. Here you see accuracy and linearity are both plus minus 1%. Possibly the instrument is inherently linear, so therefore they are stated together. See, repeatability is stated as plus minus 0.2% of full scale. That means even if you make 100 readings of the same flow, the readings will not differ by more than plus minus 0.2% of full scale. Similarly, you have say inherently linear, flow signal is inherently linear. Therefore, accuracy and linearity are specs, both are same. Actually, if it is not inherently linear, then accuracy and linearity specs will actually vary. So then there are some special other specifications which are specific to a flow sensor. For example, pressure drop is very important, because the pressure drop in the flow sensor is actually an energy loss, so it should be low. So it says that approximately 4-inch H2O. So the other factors we will not understand so much unless we really know what sort of a flow meter it is. So this brings us to the end of the lesson. So what we have done in this lesson is that we have seen why sensors are so important. We have also seen their general structure. We have looked at the static characteristic, main static characteristic parameters, and like sensitivity, linearity, accuracy, resolution, span, etc. We have also looked at the dynamic characteristic of 0th, first and second order instruments, and we have seen that they exhibit phenomena like oscillations, overshoot, they have time constants, and all these characteristics are very important, especially when these devices are used as feedback devices in control. We have also seen some industrial specifications. So before closing, we would like to have some points to ponder. So for example, what is the difference between accuracy and linearity? So when are they same and when are they different and why? What is the difference between dead zone and resolution? Which is likely to be more, dead zone or resolution? Then mention two performance parameters of control systems that are directly affected by sensors. So, and finally, what is the significance of damping in a sensor? So if you have good damping, what kind of sensor should have what kind of damping? For example, what should be the damping of an indicating instrument, and what should be the damping level, let us say, for a recorder, or what should be the damping level for a let us say a feedback sensor. So think about these, and that is all for today. Bye bye. Today we are going to look at temperature measurement. Temperature is a very important quantity, especially in the process industries. All big process plants, like chemical plants, steel plants, for them monitoring of the temperature is very important. So we will see how these measurements are done both in the online and the offline case. Looking at the instruction objectives, the first one is of course that there are various principles of operation of the different temperature sensors. So the student will be familiar with that. He or she will be able to describe the various signal conditioning aspects, as we have already discussed that measurement involves transformation from one variable to another till the measurand or the variable of interest comes into an electrical form, so that it can be used very easily. So for that you need signal conditioning and processing, and they are specific to the kind of sensors that are used. So the student will be used to describe the signal conditioning aspects. And then of course nickel and copper are much cheaper than platinum. So therefore, except in critical applications where you really need to know the temperature accurately, you do not use platinum. For example, in most of the air conditioning applications, this building air conditioning applications, people generally use nickel RTDs because of the fact that it is the cheapest, and anyway the application is not so critical. It does not demand a very high level of accuracy.